let me get my head back in the game by giving you, since I won't be playing some cool videos, a 90-second segue from the last talk. I actually did my PhD thesis in physics on technology that they're using for quantum computing now. And I promise I have a point here related to artificial intelligence. I'll try to make it in about 90 seconds. But the reason people are so excited about quantum computing is that it has the potential for exponential parallel processing speed up. So a quantum computer, as the last speaker was explaining, doesn't just have bits that are 0 and 1. They have these Schrodinger cat superposition bits, where a bit can be in some infinite superposition of zeros or ones. So the amazing thing is, with a classical computer with n bits has, let me get this right, has 2 to the n combinations in an n-bit binary memory, but it only contains n bits of information, entropic information. A quantum and so when you process it, you can only process n bits, even though they're 2 to the n combinations. Because of the superposition in a quantum computer with n bits can process 2 to the n bits of information. So a 100-bit quantum computer, that's not like the register and address space. That's the entire memory. Can process 2 to the 100 pieces of information in parallel. That's more than the atoms in the entire universe. So you get this exponential speed up from the parallel processing. Now, the comparison I want to make with deep learning and artificial intelligence is, one, we also heavily use parallel processing, typically with GPUs, for doing training of machine learning and especially deep learning algorithms. And I'm not sure I have the slides to talk about this in the talk, but deep learning and things like decision trees, once you've created a prediction algorithm, there's actually an exponential speed up. There's something in machine learning called the curse of dimensionality, that as you increase the variables, the number of data that you ingest, the computational combinations explode by sort of 2 to the n. A decision tree or a deep learning algorithm turns that on its head, and every step through the network or decision tree, it reduces the space the answer could be in exponentially. So there's actually some similarities with quantum computing. There, I got that out. And we won't see the videos. Thank you. I didn't go for clapping, but the first three slides will be very simple. Don't worry, it's just to frame the problem. It won't be one of those talks, but I don't like those. But so why should we use AI for business? This is how I want to frame the problem. What if you could predict the future? What would happen? What would you do with it? And since this is a CXO event, I want to just frame it for a few seconds in terms of the business implications. Well, in business, the way I think of it is, if you could predict the future, the AI that you would create would permeate your business. So just think of it like an income statement. It can be injected into your outward-facing, customer-facing activities, marketing, sales. It can go into your operational efficiency, and I'll show examples of all this. And most importantly, it can go into your core business engines, the way that your business, whatever it is, creates its fundamental differentiation. And as business people, we know it's the top line. Your differentiation is really your ability to generate gross margin and top line. And then, of course, operational costs. And then also risk. Risk of black swans, risk of cyber, risk of not complying, risk of failing a capital stress test if you're a bank, et cetera, et cetera. So risk to operations. So the other thing that would happen is that if you could predict the future technically with AI, or what I'll explain that it does, is that it's really two holy grails that we've created. And one is all this AI stuff, like robots and driving cars. The other is an entirely new field. It's that data science has finally matured to a level where it won't be a special department in a computer science department. Universities are starting data science departments. It's going to be on the same level as a physics or a chemistry department or an electrical engineering department. It's a whole new field. It's come of age. And what is data science? Well, the boring 10, 20, 30-second version is you've got some data, and hey, I can draw a line with it. That's statistics. That's pretty boring. It's if there's, if I have some data X, I can predict it's going to be Y. That's statistics. Like I said, pretty boring. But what if X was all the data in your Hadoop data lake, or your structured data, or all the data that you have in your enterprises, your terabytes, your petabytes of data? It's a massive differentiator, and we struggle to use it. And what if the question why that it could answer is your most important business question? That's what's at stake. And it's interesting that this problem is actually the same as the AI side, where you do robot stuff and artificial intelligence. They seem like different fields, but hopefully I'll motivate a little bit why they're similar. So yes, I promised you robot stuff, but there's no video there. So these robots would be moving around. This was a thing that Google did. And these little cheap cameras at the top watch when the robot arm picks up something. If it drops it, it trains on what to do differently, and collectively they can learn together. All these are chained together, and you can learn to manipulate and pick up objects just from learning. It's not programmed with if-then-else logic. It figures it out on its own. So before we go into the business applications, I think we're all aware, and the last talk did a great job of talking about the image recognition and video processing applications. And just as an aside, this has tremendous implications for NVIDIA because it's massive data. The business case is pretty simple. All the cities are turning into AI cities in 3, 5, 10 years. And they have all these sensors. They have 1 billion cameras by 2020. In principle, every one of them is going to need a GPU to do inferencing on the data that's coming in, prediction. And so you can do the business case, but the ramifications for society are huge. I mean, cities are going to become AI automatons. There's pros and cons to that, but it's tremendous the way it's changing the public part of society. There's all kinds of use cases. You can look at a few of them there. Vehicle detection, counting people, counting crowds, identifying faces. If there's a lost or kidnapped child, in principle, you could train on the picture from the parent and push it out to every video camera in a city and try to identify that child. Massive, really great applications. So what this would have been is a video, and NVIDIA on autonomous driving. Now, NVIDIA has a whole division. That's one application of deep learning we've decided to do end-to-end. So we have a whole developers kit. It has algorithms that can get car companies started. We're working with literally basically every car company and every startup in the world just about. And so what this would have shown you is a car driving on a neural network, the deep neural network that's been trained, and inferencing and picking things up, kind of like in the last video, at 30 frames per second. And it does an amazingly accurate job, and I think as of last year we had the record in this algorithm. But the point is that you can detect other cars, you can draw boxes around them, you can extract the lane markers, the guardrails, you can extract all sorts of things, and whether there's a car ahead of you. And so, for example, if someone's drifting out of a lane, or if they're doing something they shouldn't, like texting, and they don't see cars stopped ahead of them, you can use that information extracted by deep learning image recognition to then follow it by kind of if-then-else coding. So if there's a car rapidly approaching, apply the brakes if it's a car that's able to do that. Or don't let them change lanes because the sensor has identified there's a car in your blind spot. That's the first step of deep learning. In NVIDIA, we call that co-pilot mode, where it's just watching out for you making mistakes. The next video, maybe I'll post a version of this talk or something afterwards with the videos, but this one would have shown this car that you can see learning how to drive. That's a whole different thing. That's end-to-end deep learning and artificial intelligence. So what it does is it starts like your 16-year-old son or daughter would. It starts in a parking lot, and it's gaining experience. It's trying to imitate what human drivers do as it's given more and more training data of what a good driver, hopefully you're training with good drivers, what a good driver would do. You would see that it knocks down the cones, it learns how to navigate in a parking lot, and then out on the road, and then eventually, and this is critical, deep learning can extrapolate and generalize to things it's never seen before. So there would be a video where it drives around a construction, and it actually drives off the road because the cones are sort of indicating that you would go there. It was never trained to do that. That's end-to-end deep learning. It's using something called reinforcement learning, where the function that it's fitting, like that statistics thing, is what the human driver would have done. It's trying to figure it out. And it may have to say, well, I don't know about a construction site, but my training data shows once someone drove off the road and it didn't go well and it went well, so let me figure it out as I go along. And it would back up if it said, oh, I'm going to fall off a cliff or something like that. So let me get more into the business applications. So that's the robot stuff. That's self-driving cars, artificial intelligence, doing what a human would do. But what about predictive analytics? What about this advanced form of statistics or data science? Well, here's where it gets really interesting, because you could imagine a simple, say that this plot on the right was a housing model. You'd say that, well, the house price could be predicted by the square feet. Yeah, that would probably give you some kind of a linear correlation, but you know that the neighborhood, location is important, all kinds of things. Well, mortgage risk, you could start with one or two variables like the FICO score and whether the person has currently employed. But here's a mortgage deep learning model that drew from a portfolio of 2 million individual loans, and it used a deep learning model to train on 300, and it could do more, but 300 potentially explanatory variables. Exogenous data, the origination data of the loan, but also the performance data of the loan. Were certain types of loans delinquent month by month? Were they paid off, meaning they were refinanced, which is very important for cash flow? And long story short, the deep learning model here is predicting the prepayment amount in the portfolio. So on the x-axis is the actual number of prepayments in a portfolio of 1,000 loans chosen out of a 2 million loan candidate pool. And on the y-axis is the actual prediction. The black line is perfect, 100% perfect prediction. And you can see the blue neural network model is glued to perfect prediction, and the red is a simpler statistical logistic regression model. Another case of that in inventory management. So these bars are some product, I think it was something very simple like bottled water. The gray bars are the actual demand week by week from one of the biggest retailers. And the black line is the predictive model from standard predictive analytics that frankly is historical. It's backward looking. To me, that black line is just noise that's going straight across. It doesn't seem to be very predictive. What they did, and this was work by IBM actually, it's cut off down there, but they merged in with a deep learning model along with the inventory data and structured database, exogenous data predicting things like week ahead weather forecasts and things from Twitter, like maybe people are tweeting that there's a county fair or something. And so the deep learning model figured out that the week ahead weather forecast was hot and said, well, okay, people drink water when it's hot. And in fact, there was a spike, a large spike. That's that thing at the far right, bottled water. And the red deep learning model, look, it predicted it. Now, that's some people say, wow, and other people laugh when I show that example. Because they're like, of course, it's hot, people drink water. But then I remind them that the biggest retailer has 100 or 200 million product SKUs, and try getting people in a room and predicting the up and down demand of those hundreds of millions of SKUs in every condition, in every store, with every preference. Maybe there's 18 types of bottled water. It predicted the type of bottled water they want at that particular store. It's not generic. And this retailer called this one of about $6 billion business problems they had that machine learning could solve. I'm going to speed up. But so this predictive analytics is being used in insurance, and one of the use cases, just to give you an example, can't always show real data because it's often confidential. The slides were cut off a bit here. But it's to take satellite imagery and then actually put in historical weather data. And then what you do is you train a model with labeled data, which is the historical yield. And so you actually build an artificial intelligence model, and you train it to recognize from past years when the crops look like this, maybe in visible images and infrared satellite imagery that can tell things about the temperature of the ground, and the historical weather, the yield that I got from this farm is a certain amount. So imagine that you could predict the risk and the cost if you're an insurance company of crop insurance. Apparently it's like a $20 or $30 billion a year insurance market. So this is a core thing in your business, if you're an insurance company, is predicting the pure premium, the cost that you would expect to pay out, so that you can write a policy meeting the margin requirements you want, and basically potentially undercut your competitors, still meet your margin, and you'll get elastic extra market share. This is an example that is going to be going into production. This was from a research hospital. But one thing happens in emergency rooms is a patient will come in and they'll be crashing, and they can't figure out why. There's something that they're not understanding. And they hook up the standard things like just blood pressure and respiration and heart rate, not that complicated. So this was taken, those vitals were put into an image in a convolutional neural network, and these were people, this patient group unfortunately were ones that crashed and died in the emergency room. And you can see the probability of survival in that red in the lower right is being predicted. Now, you might say, okay, who cares? But the point is that you can escalate and understand how long you have, and then the next step, which people are working on, is to predict what you need to do to bring them out and predict what the problem is. And I'll show you another slide with that. But so this is going to be massively huge in medicine. So that's another business case. The image detection, there was another step that was taken a few years ago where you can do things. You've probably seen this. You can label images. Here the computer is taught to label images. These use cases are propagating very fast from academia. This was a paper at Stanford, I think only 3 years ago. Within less than a year, or about a year, some people in medical radiology research took that code, and the sharing of code, we're at this open data science forum, the openness is incredibly important because someone was able to take this code off GitHub, run it in TensorFlow or Caffe or whatever it was, and then say, well, if I can predict that that's a black cat sitting on top of a suitcase, I can probably replicate the radiologist generated annotation, and it basically, it works. So this is quite remarkable what that's a deep learning case, what deep learning can do. Here's an example for diagnoses where not in the emergency room, the situation where someone is crashing, someone might go to their doctor and they ingest all of the information, your patient history, but again, you're comparing against known cases that have been trained on from the past, potentially hundreds of millions. And this is from a startup, and they're basically saying that, hey, you've got a certain probability of congestive heart failure. Today, you're in my office, it's 72%. There's a 91% chance that you're going to die in 3 years. You better do something to change this. This is your future. So it's win-win. If you're the patient, you want to know that. And if you're the insurance company, you want to correct it. You can help have a good outcome and also avoid, a costly medical treatment. So I don't have much time, but I'll go through this real quickly. The real game changer, which is this new field of data science, is that previously what we do with our data in a big Fortune 500 or Fortune 1000 or a large enterprise is we have these structured databases and these unstructured Hadoop data lakes with terabytes and petabytes of data. And we do all kinds of historical averaging, queries, averaging database stuff. We get insights into what happened in the past. But the thing about predictive analytics and AI is it tells you what happened in the future. That's actually not that different. Sorry, but I'm going to digress and make this point with scientific theory, except that with things like physics and chemistry and deterministic engineering, people basically guess the model. They say this is the way that fluid flow works. They build a model with some fancy equation, differential equation or whatever, and then, yeah, they go and validate it because it's the scientific method. Maybe they fit a small number of parameters, like 3 parameters, and now they have a prediction model. That's what we call science. Guess what? We now have a business theory, sort of like on the same status as engineering, or maybe not quite physics or chemistry or engineering, but this is data science. But it's interesting, it turns this around. People like Einstein didn't guess special relativity and then prove it and say, well, if the data is wrong, then I'm sorry for God because my theory is right. That's what Einstein said. But you start with the data first in data science. You build the model, and often it has billions of parameters. It's fitting all the data in your Hadoop data lake, and now you can do a prediction. But now this prediction fits into your business with things that you could never accurately predict before. You can predict the airflow over an Airbus jet by doing these fancy differential equations and high-performance computing. Now you can do high-performance computing with deep learning to predict all these things I've been showing you in your business. So let me wrap it up here. So that's predictive analytics. I guess one last slide here. I won't get into this, but some of you probably recognize this is the tremendously mind-numbing and complex diagram, and this is just a simple version of a Lambda architecture with a batch mode and a streaming mode where you ingest data, you have a Hadoop data lake, you can have a speed layer like Spark and a serving layer like Cassandra, or you can have proprietary solutions. And it's very complicated, it's hard to maintain, and again, the challenge is that you get a snapshot of the past, you get the history. Data science and artificial intelligence is a new paradigm for big data. What it is you get this virtual cycle where you use the big data, you train models that can predict the future, and then you deploy those models, you plug them into your data center, and those answer your most hard, your most thorny, your most challenging business questions. And it's a virtuous cycle because your models only get better and better with more data, and you can collect data from the endpoints all the way out at the edge of the cloud. And so I think I want to end with just one slide here. Sorry, I really had to skip a lot. But I hope I sort of motivated this slide that you can plug in solutions to your hardest, your thorniest business problems everywhere. And it's going to massively improve the profitability of your business, the success and the happiness that you have with your customers. And as a last little shameless pitch for 15 seconds, well, first of all, if you're really interested in learning about GPUs, which power the deep learning and the AI revolution, we have our technology conference next week. So if you want to fly out to San Jose and Silicon Valley, there's still space available. And we have a deep learning appliance, which is a supercomputer in a box called the DGX-1. It's 8 of our latest GPUs, and this is 170 teraflops of half-precision power. That box, which is 3U, it's this big, is more teraflops computing power than the most powerful supercomputer in the world was in 2004. It was a machine in Japan called the Earth Simulator. It had its own building. It was a $1 or $2 billion machine. And this 3U box is now more powerful, and it's needed. You can run an entire starting up data science team on this, and a data science team of 100 on a number of these. So I encourage you to contact us if you want to know more, and encourage you to attend GTC now or next year. Thanks.
Thank you. Thank you very much, Andy. Thank you. That was absolutely fascinating.